All right, so in this video, we're going to build up some ideas that's going to help us to transition into a lengthy conversation about curvature and acceleration. So to get things started, we're going to begin with arc length. Now, the arc length formula for a vector valued function is up on the screen, and you'll see that even if we weren't in vector valued form, we could use the parameterizations of x and y as functions of t like we did in Calc 2, and this first part right here would be the same arc length formula that you would have seen in Calc 2. We're now just carrying it on to a z component as well, so we have the dz dt quantity squared underneath that radical. Now, again, nothing really surprising with this at all, but it's interesting. So if we observe that r prime of t, which is equal to v of t, is going to be dx dt, dy dt, and dz dt. So all I've done there is took the derivative of this, and we know that we go component by component, so derivative of x with respect to t, y with respect to t, and z with respect to t. And we've also noted now that this is the velocity vector since it's the derivative of the position vector. Now, this is also, right here, the magnitude of this vector. Right? So if we take the magnitude of this, meaning we take each of these, square it, add it together, and then underneath the radical, that's going to be the magnitude of the velocity vector. So what we can say is that the arc length s is going to be nothing more than the magnitude of the velocity vector. And that's an important one to hang on to. That's one of those formulas that will keep appearing throughout the course. All right, so now we're ready to talk about an arc length parameterization. So now, if you remember, and you can see with the example up on the screen here, this is a parameterization of a curve, and the parameter is t. T generally denotes time. We think about it as when time is 2, let's say the particles travel 2 seconds, where is the particle now? Generally, that's how I'll describe that. And so we're going to transition now a little bit and not parameterize based upon t or time, but instead specifically for arc length. And so where is the particle if it's traveled an arc length of something, okay? An arc length distance of something. And so we're going to start from the point negative 5, 0, 5. We always need a place to start so that we can then measure the arc length. So our goal here is to essentially change these t's into s's. Now to do this, fortunately it's not too difficult most of the time. We just need to remember that s is going to be the integral of the magnitude of the velocity vector. Okay, so now don't get weighted down by the notation here. Our vector here, r of t, can easily be written as negative 5 plus 3t, 2t, and 5 plus t, which means that the derivative of that, being our velocity vector, is going to be nothing more than 3, 2, and 1. So when we take now the magnitude of the velocity vector, that's going to be the square root of 9 plus 4 plus 1, which is just the square root of 14. And so I'm going to replace the magnitude of v there with just the square root of 14. So s equals, and it's important, I'm going to keep this s equals going down, the integral square root of 14 dt. And when I integrate this now, I'll get s equals the square root of 14 t. Well, remember what our goal was. Our goal was to replace all of the t's with s's. And so if I solve this for t, now I'm going to be able to substitute in as needed. So that means our t is going to be s over root 14, which means that our parameterization now, and I'm going to write this as x of s, just to be clear, would be negative 5 plus 3 times s over root 14. Y of s now would be 2 times s over root 14, and z of s would be a 5 plus s over root 14. So that would be the parameterization. And let me go ahead and just say it again because it is kind of a strange transition from time to arc length. But just remember, if we've got a curve here and we want to say that, where we're using t's and t stands for time, at time equals 0, we're going to be, let's say, here. At time equals 1, the particle has continued to travel, and maybe we're here. Time equals 5, it's continued, and it's pointing to this point here. So that one's a pretty intuitive one to understand. The arc length one is similar in the sense that it needs to start somewhere. So we're starting from negative 5, 0, 5. Let's suppose that this is our point, negative 5, 0, 5. Then when I plug a value in for s, let's say a 1, that's going to say the arc length is 1, meaning 1 distance here to get to our new point. Same thing for y and z, of course. When the arc length is 2, it's going to point us up here to a new point. When the arc length is 5, it's going to point us to a new point up here as well. So we're just dependent upon a different criteria in order to map out these same points. All right, so now we're ready to talk about unit tangents and unit normals. We'll start with the unit tangent vector, and it's really not a surprise as to what this is going to be. If we've got our curve C, if we've got our vector valued function r of t, then we're going to go ahead and construct a tangent vector at this point. We all know that the tangent vector now is the derivative. And so I'll go ahead and sketch this up here. And this is also where I always need to say those two vectors, the blue one and the red one. So let me mark this as this thing here. As you look at those vectors, sometimes when I draw them, they appear to be perpendicular. They're not necessarily perpendicular. The only time that they are is if r has a constant norm. And we've addressed that in the past, and we'll address it again here in just a little bit. But just to remind you, those are not necessarily orthogonal. So anyway, this is our tangent vector at this point, but it's not necessarily a unit vector. And so we want to make sure that the actual unit tangent is, in fact, a unit vector. So all we're going to need to do now is normalize r prime. So capital T of t will stand for our unit vector, and that's just going to be the velocity vector normalized. You can also see it written as r prime of t divided by the magnitude of r prime of t. Both of those are clearly the same thing. I've labeled them here, right here. So whichever one you prefer to look at, whichever one you prefer to deal with is perfectly fine. So that's going to be your unit tangent. Now, for the unit normal, let me go ahead and draw a similar picture, kind of get us started here. This will be our curve C, and we've already established that we have this unit tangent right here. So that's going to be our unit tangent. Now, the unit normal that we're talking about is going to be this guy right here. And it's going to now be to the effect that these two vectors are in fact perpendicular to each other. Now, I want to make note a little more formally than I've mentioned before. We can say that if vector t has a constant norm, then vector t is going to be perpendicular with t prime. Okay, that's what I was saying up here about how these are not necessarily perpendicular. The only time that they are, in fact, is if this vector has a constant norm. Well, in this case, it is going to work out that this vector and this vector are perpendicular, and this being t prime. We can say that with confidence now because t has a constant norm. The constant norm of t is going to be 1 because it's a unit tangent. So since that has a constant norm, when we take the derivative of it, t and t prime are going to be perpendicular each time. Okay, and so this is going to be our normal vector. It's not quite a unit normal, and so we're going to have to normalize just like we did up here. So if I go ahead now and draw in there this guy right here, that is going to be our unit normal. So our unit normal, n, is going to be the derivative of t divided by the magnitude of t. And I said t prime it is. T prime, you can see it marked on here, I apologize. So the magnitude, or the t prime divided by the magnitude of t prime to normalize this vector and come up with the yellow one. Okay, so this idea right here, it comes full circle. We talked about it a few sections ago, and now we're taking full advantage of it. Since this guy has a constant norm, we know that when we take its derivative, that vector is going to truly be orthogonal to it.